We're going to take a look at polynomial graphs, the graphs of polynomial functions, and our objective today is to identify key characteristics that are specific to polynomial graphs. So by definition, a polynomial graph should be smooth and continuous. And I have some examples and some non-examples on this slide. So a polynomial graph is smooth and continuous. Notice that these graphs in blue are both smooth and continuous. So I can trace each of these graphs, each of these curves, without lifting up my pencil. So that makes it continuous. And they are smooth as opposed to not smooth, like this one right here. We'll call this A. Example A right here is not smooth because I have a sharp corner. So all of these humps, all of these are rounded. So that's what makes it a polynomial graph. As opposed to B, we'll call this one B over here. This one is not continuous because I do have a break. There's a break at x equals 0. So there's a break, it's split into two different parts. It is continuous, it is smooth, however, it is not continuous. And same with this one over here. Down here, I'll call this one C. I have a jump here. There's a jump. I can also describe that as a break. So my graph does break. My graph is split into two separate parts. So these are not polynomial graphs. This one has a sharp corner, so it's not smooth. This one is broken into two different pieces, so it is not continuous. And C is also broken into two different pieces, so it is not continuous there either. They must meet both of these requirements, such as these graphs on the left side in blue. They are both smooth and continuous. Therefore, they are graphs of polynomial functions. So let's look at our first example here, graph A. I know that this is a graph of a polynomial function because it is both smooth and continuous. And then if I look at the equation, I recall that the definition of a polynomial has to have, the exponents must be positive whole number exponents. And they are. So this is in fact a polynomial function. So let's look at the domain. Okay, remember the domain goes from left to right. So what is the point that is farthest to the left that this graph will go to? It would be negative infinity. And then what is the point farthest to the right that this graph will go to? Remember these have arrows, so they continue on forever and ever and ever. So this is going to go forever in the downward direction, but it is also going to go on forever in the right direction. So it is also going to approach positive infinity eventually. Okay, now the range goes from bottom to top. So what is the lowest point this graph will reach? Negative infinity. It keeps going on forever in the downward direction. And what is the highest point that this graph will reach? Again, positive infinity, since it is pointing up toward the positive infinity direction. Our y-intercept. Where does this graph cross the y-axis? It crosses it at -1. My interval of increase. So if I were to draw a little person here in a roller coaster car, he's going to go, and we're moving from left to right. He's going to go down, 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 and then turns around at this point, starts coming back up, and then turns around again at this point and starts dropping down. One more time. So he starts increasing at this point right here at this interval. So I want to know what x values I'm looking at. So I'm looking at from -1 to 0. I'm just looking at this little piece right here where it starts increasing again. So I write it in parentheses using only parentheses for intervals of increase and decrease. We're going from -1 to 0 where it is increasing. Now my intervals of decrease, so where is he going downhill on that roller coaster? Well, he's going downhill from here to here. So we're looking at negative infinity. So it's from the left side up to this point right here. So from the left side, from negative infinity to that point right here, that x value, that is -1. And then it started going back down again on this piece of my graph. So that is from 0, we're looking at the x value, remember what x value is at? 0 all the way to the right. So the right means positive infinity. So from 0 to positive infinity, we are also decreasing. Now let me take all this away because it's getting distracting me from looking at my graph. Okay, now the zeros. So these are the new things that we have, the new characteristics specific to our polynomial graphs. So I have the behavior at the zeros. First I need to find my zeros. Remember, the zeros are your x-intercepts or roots. Where does the graph cross the x-axis? I'm going to estimate that it's about negative 1.8. X equals negative 1.8. And remember, we only have 3 options for behavior at zeros. So let's take a look at our behavior at 0. So for example, this graph shows all 3 different kinds of behavior at the zeros. At this point right here, the first point, we see that it crosses straight through. So it crosses through the x-axis, and it'll cross straight through. At this point over here, we'll call this number 2, we see that the graph bounces off the x-axis, so we describe this behavior as touching and turning around. So it touches and turns around at this point. We can also call it a turning point. At this last 0, we'll call this 3, it goes through with a little bit of it wiggles through the x-axis, but we call that a point of inflection. So it goes through with an inflection. Okay, we can call this an inflection point. Okay, so let's continue on our graph over here. So our zeros, the behavior at this 0 in particular, we're looking at just crossing through, crossing straight through. And now for the end behavior. The end behavior, I'm looking at the little arms, the little ends, each end of my graph. And very simple, we call this the left side. We call this the right side. So all I'm going to say is it either up or down on the left side, or is it up or down on the right side? So I see that on the left side of my graph it goes up. So very simply I'm going to describe it as left side goes up. And then on the right side I see that the arrow points down. So very basically just describe the end behavior. The right side goes down. Okay, relative min and relative max, I'm looking at the humps. So we're looking at, let's see, we have a hump here and another hump here. So which one is the minimum and which one is the maximum? This one is your minimum right here. We're looking at the point -1, -2. And this one is my maximum right here. We're looking at the point 0, -1. And I am now done describing the behavior of my polynomial. Okay, this is a polynomial graph because it is both smooth and continuous. If I look at the equation of my polynomial function, I see that the exponents are positive whole numbers. Therefore, this is an equation of a polynomial. And I see that my polynomial is in standard form because my degrees go from highest to smallest. So now I am done describing my polynomial graph. I have another example here, graph F. Let's take a look at this one and find all the key characteristics of this polynomial function. This is a polynomial function because it is both smooth and continuous. So let's find the domain. Again, domain goes from left to right. So the point farthest to the left that this graph will ever travel to will be -infinity. And then the point farthest to the right that this graph will travel to will be positive infinity. My range goes from bottom to top. So the lowest point that this graph is going to go to is, look at the arrows, they go down forever. So it's going to be -infinity. However, the highest point is this point right here, so I'm looking at maybe 3.1, 3.2, so 3.2 with a bracket, because that point is included. Now the y-intercept is going to be about negative 3.9. It is increasing at several different intervals, so again, if I were to draw a little guy on a roller coaster cart, we're going to go up, going to go up, going to go up, going to go up, then downhill, then up again, then downhill again. So you have to find those intervals on which it's going to increase. So we are looking at from here to here and here to there. And so remember, we look at our x values. So chop that right here. So from the left side up into this point, we're going to call the left side negative infinity. Up to this point on the x-axis, I'm going to call that negative 1.5. And then it starts about here. So what value is that on the x-axis? I missed a little bit. Let's try that again. Right here. What value is that on the x-axis? I'm going to call that maybe negative 0.2, comma 2. Let's see. It stops increasing here. That's where it starts turning around again. And I'm going to call that point, or that it is on positive 1. So where is it decreasing? On the other intervals in between. So let's take a look at those intervals. So we're decreasing from this point to that point, and this section is between these two red dotted lines. So we're going from negative 1.5 to negative 0.2. And it is also decreasing from this point here on forever to the right side. So this point is negative 1 or positive 1 to infinity. It's decreasing, or yeah, decreasing. So positive 1 to infinity, we are decreasing. Now I'm going to erase all of this because it's distracting me to see the rest of my answer. So I'm looking at zeros now. So I have a 0 at negative 2, I have a 0 at negative 1, and I have a 0 at positive 1. So x equals negative 2, negative 1, and positive 1. So what is the behavior at each of these zeros? Well, let's take a look. At negative 2, at x equals negative 2, it crosses straight through. Okay, at negative 1, at x equals negative 1, it also crosses straight through. And then at positive 1, it touches and turns back around. So at x equals positive 1, touches and turns around. Okay, so that's it for end behavior, or for behavior at the zeros. Now my end behavior, let's look at the ends. So I have a left side and I have a right side. What direction does the left side point? Down. What direction does the right side point? Also down. So we can say both left and right go down. Super mathematical and technical, I know. So our relative minimum, okay, so I have only one that curves under like this. So that's my relative minimum. And what point is that? Let me see. We are at about negative 0.2, comma, our y is 4, negative 4. Our relative maximum, so I have two humps that curve over like this. So which one is the maximum? Which one is the highest? This one up here. Okay, not this one, but this point up here, which I'm going to call negative 1.53. And the degree of this polynomial is a little bit different because I don't see it multiplied out, and I don't need to multiply it out. I just have to keep track of how many x's I have in my head. So if I were to multiply this out, you know, I'd get x minus 1 times x minus 1. Well, I already know that x times x is x squared, so I have 2 x's there, then 3, then 4. So my degree is actually 4. If I were to multiply it all out, I would get negative 2x to the 4th plus minus stuff and more stuff, but I don't care about those. I just care about the highest one, which would be 4. So that's it for today.